We've now covered 2 of the 3 topics from the course. First topic was about infinite sequences and series. Second topic was about differential equation. And now the last one, Laplace transforms. This particular topic is truly different than anything you've seen before in calculus. But it is indispensable. Let me give a couple of remarks about problems that we've solved before and show you that if I slightly modified them, I would not be able to solve them without Laplace transforms. And what I'm thinking about is differential equations. Laplace transforms are used in a lot of areas of mathematics, engineering, any applied mathematics. Laplace transforms often arise. Our attention is simply going to be connected to differential equations. What we're going to do is solve all of those linear differential equations that we saw in chapter 15, but we're going to go beyond that. Because if all the Laplace transform did was simply solve the problem that I've solved before, why bother? But let me indicate to you where stuff we saw in chapter 15 falls down. Oh, by the way, Calculus book does not contain this material. You go to the webpage for the course, and you'll see in there Laplace transform notes probably, all right? And then you're going to see Laplace transform solutions. So everything that I'm going to talk about comes from those notes on the web page, and there are solutions to every problem in the chapter. Now, it is called chapter 6 rather than chapter 16, simply because this is coming from my book on differential equations. So you have to live with 6 instead of 16. Consider once upon a time, back in section 15.3, we talked about tanks. We had some stuff coming in, there was some salt in here originally, and then we had some more salt coming in at a concentration. At the same time, we were taking it out, and we were asked, find how much salt is in that tank at any given time. And we set up linear differential equations of first order to solve that problem. Right? But suppose the following happens. Suppose it's coming at a certain concentration C1 and a certain rate R1. And I say, oh, I want to change one of those. I either want to change the concentration of the salt coming in, or I want to change the rate the salt is coming in, or that solution is coming in. So now I've got a new problem. I've changed how fast the salt is coming in. So what would I have to do? Suppose this happened at time t1. What I would have to do is I'd have to solve this problem with the first concentration up to time t1, and then reconstitute the differential equation after t1 because I got a different rate that salt's coming in. Maybe after time t2, I change it again. So now I have to change the differential equation again. This is a pain. Laplace transforms gets you out of it. You don't have to keep changing the differential equations. Laplace says, I'll take care of that for you. Suppose the following happened, that I was standing here with my bucket and I suddenly dropped a whole bunch of salt in. Oh, how am I going to handle that? And the answer is, I cannot handle it at all. Right? The first one, when I had the various concentrations, I can handle it, but it's not very convenient. In fact, right, everything that I did in chapter 15, all that linear stuff, every right-hand side of the differential equation was continuous. If you go to exercises 26 and 27, in 15.9, I introduced this idea where that non-homogeneity had 2 different cases. From 0 to x it was something, or from 0 to 1 maybe, and then from 1 to 5, whatever, it was different. And I illustrated there how you handle it. It's not convenient. It's the same idea as here. You have to do the differential equation up to t1, then you have to do it between t1 and t2, then you have to do it after t2. All right? Handleable by 15, not convenient. But if I drop a whole bunch of this stuff in, suddenly, chapter 15 says, I cannot handle that. Laplace says, I can. So you can see for that particular scenario, Laplace transforms are necessary if I go beyond the situation in chapter 15. Consider the following. Suppose I've got an LCR circuit here. Right, so you got a capacitance, you got electromotive force, you got a resistance, you got an inductance, and you got a switch here. All right? And some silly idiot comes along and says, I'm gonna play with the switch. I'm gonna go up and down, up and down, up and down. Well, suddenly this electromotive force is there, and then it's gone. Then it's there, then it's gone. What do you have to do, chapter 15? Keep solving. While it's on, you solve this. While it's off, you solve that. When it's on, you solve this. And you have to keep doing it over and over and over again. Laplace says, no, you don't. I can do that. Right? Consider a vibrating mass spring system. Mass, K, maybe some damping, all right? And you get it going, and suddenly you say, I'm going to whack this thing with a hammer. Chapter 15 says, I don't know how to handle that. I don't know how to model a whack. Laplace says, I do. I can handle it for you. So you can see those are scenarios that are not handleable at all or very inconveniently with what we learned in chapter 15. But Laplace takes care of all of these very efficiently. So there's a lead-in why we need Laplace transforms. Laplace transforms are one of many integral transforms in mathematics. There are all kinds of them. Depending upon the type of problem you're solving, you get a transform from that kind of problem, a different transform from that kind of problem, different transform from that. You engineer electricals will see not only Laplace transforms, you will see Fourier transforms. And there are things called finite Fourier transforms. And there are things called Mellin transforms. And there are called things called Z transforms. Each one a particular important in a particular application. They all look like the following. They take a function f of t, and they multiply it by some function called k of s of t. And this guy's called the kernel. And he's given to you. And then what you do is you integrate this thing from somewhere to somewhere. And it produces it. If you integrate with respect to t's, the s's will survive, and you call this an f. So this guy's called the transform of that function there. So what the transform does is takes functions of t and then turns it into functions of s. And it depends upon what this k is, what transform you're talking about. For Laplace, this guy is e to the minus st. The kernel for Laplace. So in other words, we have the definition. Definition. B. Laplace transform of a function f of t. Well, let's just write f of t is f of s. And you often write this, that f of s is equal to the Laplace transform of f of t. So when you see this curly L, that says you're taking the Laplace transform of the function in the curly brackets, right? Is f of s. Where f of s is equal to the integral from 0 to infinity. So a has become 0 and b has become infinity, and we're putting that kernel in here, e to the minus st, f of t, dt. So that's what you mean by the Laplace transform of a function. Now, there's a big problem not all functions have Laplace transforms. And when you get Laplace transform of a function, it doesn't exist for all values of s. There's only certain values of s for which it exists. So when you go and do this, you're finding then the values of s for which Laplace transforms exist, if it exists. And this is, I'm not sure you studied these in first year, and I don't think you did. They're called improper integrals. And improper integrals, if you want to learn about them, and you should learn something about them, are discussed in chapter 7. There's a section in there called improper integrals. All right? So you should study them, because every Laplace transform is defined as an improper interval. All right, some comments that I've got to make before we start doing them. As I said, the Laplace transform never exists for all values of s. There will be some number, alpha, such that s's will have to be bigger than that, and we may have to discover what the alpha is. That is, then, the values of f of s will only be defined for s bigger than that number. I will be using t's. In this whole chapter, I'll be using t's, and I'm probably going to think about t as being time, but don't get the idea that it has to be. For all electricals, all right, and if I'm solving this problem here, it's got t in it. If I'm solving this, I've got t's in it. If I'm solving this, I've got t's in it, right? But don't get the idea that Laplace transforms only transform functions of t. There is a section in the notes, but I did not include it on the webpage, on solving beam deflections using Laplace transforms. And there's no time in there. There's just this beam bending under various forces. And that can be solved for the deflection using Laplace transform. No t's, just x's. Right? But most of our work, especially like problems like that, will be that t will be time. Right? So we'll constantly say that, but I remind you, it doesn't have to be time. Another point to make. Units. What are the units of f of s going to be? T is in time, perhaps in seconds. When integration is simply an addition, it does not change units. Right? All right. But what have we got here? This. What are the units of that? Problem is, that's a problem. What are the units of e to a minus s times a t? Well, this guy has units of time. This guy really can't have any units. Because if you thought about the expansion of this guy in terms of, say, Maclaurin series, then you'd have a whole bunch of things. And you'd have STs and S squared T squares and S cubed T cubes. And that's not going to have very nice units unless this guy doesn't have any units at all. So if that guy doesn't have any units at all, if this one's in seconds, this one's got to be 1 over seconds. Then the exponent will not have any units, and therefore this does not have any units, all right? And therefore we can say, so S then is, if you like, in the frequency domain. It's 1 over time. And that is indeed true. Especially for your electricals, when you start talking about that, right? The Laplace transform is in the frequency domain. It's a function of the frequency. All right, what else? We always use, or we will always use, a small letter for the function that we're going to transform, and we will use its counterpart for the transform of it. So we take transforms of small f's, and we produce big F's. We'll agree to do that throughout this whole chapter. Now, that is an improper integral, and if I were going to do things properly, I should probably do the following thing. Suppose that, say, g of s and t is an antiderivative of e to the minus st, f of t, with respect to t, because we are integrating with respect to t. So suppose an antiderivative of this thing is this thing here. Then what we would write, we would say, by definition, what you mean by the integral from 0 to infinity of e to the minus st, f of t dt, you mean integrate from 0 to capital T of this same thing. And then you take the limit as big T goes to infinity. That's the way improper integrals are defined. You go and do that. All right? So what we would do here is that we say, well, an antiderivative of this is that, so we'll take the limit as t approaches infinity, and we'll take that g of s and t, and we will drop in 0, and we will drop in t, because that's how you do this. And so then you would write the limit as t approaches infinity of g of s and big T minus g at big S and 0. And this one doesn't have any t's in it, but so you can take that out. That's what we should write mathematically if we wanted to be very, very sticky. We're not going to do that. We're simply going to write instead. Instead, we write that the integral from 0 to infinity, e to the minus st, f of t dt, is equal to, just like at first, you take the antiderivative, g of s and t, you drop in 0 and you drop in infinity. So we'll write that, but we know what that means. This means take the limit as t goes to infinity of this. That's what this said very formally. We're going to write this and say, that's what we do. We find an antiderivative, there it is, we plug in 0, and we take the limit as t goes to infinity, and then we subtract it 0. Just to avoid all the notation and writing. But that's what we understand. Clear then? So we'll see this over and over and over again. And that's the way we're going to write. Now, the first thing that you might not, one other thing. For our purposes, S is going to be real, right? But if you progress far enough in learning Laplace transforms, and your electricals might do it anyway, right? S can be complex, in which case then this is a complex function, it is not real. But for basically most of the work we will be doing, we will think about S as being a real variable, and then f of s is a real function of that real variable, s. But in advanced work, it is necessary, right? If I'm doing ordinary differential equations, that's what we're doing. That's good enough. But if you want to talk about partial differential equations, then use Laplace transforms, then you must talk about S being complex. Must. So it depends upon how far you're going, whether you can live with reals, or whether you have to go to complexes. But for our purposes, it will be real. Now, as a mathematician, the first thing I would ask is, for what kind of functions do Laplace transform exist? Does the Laplace transform of any function whatsoever exist? And the answer is no. Only certain kinds of functions have Laplace transforms. And so my first objective might be to say, All right, what are the conditions on F in order that it will be guaranteed to have a Laplace transform? So I'm going to do 3 examples. They're going to point us in the correct direction on what kind of properties the F must have to have a transform. So it's 3 simple examples. First one, find the Laplace transform of f of t equal a nice simple little function t. Right? Well, by definition, the Laplace transform has values. Integral 0 to infinity t e to the minus st dt. Now a comment based upon, this is a particular one, but if you reflect back onto what you had in the first year, forget about the limits for a second, and I said go find an antiderivative. Do you not recall that it doesn't seem to matter what you put here, if that exponential is there, no matter what you put here, it's going to be integration by parts. And that's just about always true. That every time you want to find the Laplace transform of a function, by using its definition, you're almost always going to be doing integration by parts. And in particular here, we would probably say one of these guys is going to be u and the other one's going to be dv. What will we do? First here says, put into the dv the most complicated part of the integrand that you can integrate in your head. Well, I think it's that one. I can integrate that guy in my head. If you can't, you're in big trouble. All right? So you've got it. And therefore, u is going to be equal to the t. I need the du, that's a dt. V is equal to e to the minus st over minus s. That's the antiderivative of that in our heads. So we can now say you are equal to, we're going to use integration by parts. What do we write? u v t o e to the minus st over minus s. And what do? We go 0 to infinity minus the integral 0 to infinity v du. So e to the minus st over minus s dt. So there's what we're looking at then if we use integration by parts. So let's talk about the first one. I had no problem with this. Remember, I'm integrating back to t, so that t is going to go there, and therefore it's gone. I'm supposed to now take the limit of this as t goes to infinity. Don't have to look at the bottom. But if t goes to infinity, that was getting large. What is this one doing? And that's the whole point. What is that doing? Well, if s itself were negative, then this would be positive and the limit would be infinity. So we don't want s to be negative. We want this Laplace transform to exist. And remember, I have to find out the values for which it does exist. Well, what if s, I can't put s equal to 0 either, because I'd have a big problem with the denominator. What if s is greater than 0? What is this going to do? Well, if s is greater than 0, then this is e to the minus something, and t is getting huge. What is e to the minus a huge? And the answer is 0. So this one is going to 0, provided s is bigger than 0. So we know so far that the Laplace transform of this guy can only exist when s is bigger than 0. We still haven't finished. We still have to do this. Maybe there's some more restrictions. I don't know. Well, let's see. We've canceled that with that. We would integrate again e to the minus st over now s squared from 0 to infinity. But if s is bigger than 0, we got that same guy. This is going to 0 for the infinity. Now we have to substitute in t equal to 0 and subtract, all right? Except I forgot a minus sign. When I integrated this one, I forgot that minus sign. So if you subtract, you get then 1 over s squared. There's the Laplace transform of t. It's 1 over s squared, but only for s bigger than 0. Right? So there's our first example. Second example, even easier than that one. Find the Laplace transform of f of t. Find the Laplace transform of e to the at. A constant. Right? Find the Laplace transform of that. Well, by definition, f of s is equal to integral 0 to infinity e to the at e to the minus st dt. I can join the exponentials together. Integral 0 to infinity e to the a minus st dt. I can integrate that in my head. All right? It's like e to a constant times t is not the antiderivative e to the a minus s over a minus s. And we're going to put in 0, and we're going to put in infinity. Right? All right, let's think about the infinity part. The infinity part. I don't want this to blow up. Right? Oops, I forgot something. I forgot my t's. All right, I forgot that t there. I don't want this to blow up when t gets large. That will happen. All right? It will blow up if s is bigger than a, and that's positive. Therefore, I want this to go away. I need the s to be bigger than a. All right, here it comes. S is going to have to be bigger than a. And in that case, that's gone. And now all we have to do is put in t equal to 0 and subtract because it's a lower limit. So if we put in that, we get 1 over s minus a. There's the transform of e to the at. 1 over s minus a, but only for these values of a. Only defined for those. You cannot take this thing, it looks like you can do it, all right? I can plug any s in there I want except equals a, but it won't be the transform of this guy. It's only the transform of this guy when s is bigger than a. Third one, I'm going to simply talk about the one in the book as an example, because I don't want to do all the calculation. I want to get the essence of it. So it's example number 3. Example (6.3). It asks you to find the Laplace transform of this function. F of t is equal to 2t squared from 0 up to 1, and then 1 for t bigger than 1. So if you drew a picture of this function, it's a problem up to 1, in which case it would be too high, and then it is 1 thereafter. That's 1 high. So what we've got then is a discontinuous function to find the Laplace transform of. And that's reminiscent. Remember when I had that tag back there, right? And I wanted to keep changing the concentration or the amount, the rate at which salt was coming in. I would have a discontinuous function. This is trying to prepare the way for doing that. Well, by definition, f of s is equal to the integral 0 to infinity e to the minus st f of t dt. But because my integration, or my function, is got 2 different definitions, I would have to break my integration from 0 to 1, and then from 1 to infinity. And from 0 to 1, I will be putting in 2t squared, e to the minus st dt. And from 1 to infinity, I would simply be putting in 1. I'd have e to the minus s dt. So I'd have to do these two integrals then to find out what the Laplace transform of this function is. This one we can do on our heads. This one we would have to do two integration by parts, and I don't want to do that. So I'm going to tell you what the answer is. Right? According to my notes, the answer when you're all finished doing those integrations by parts, and so what you get, minus 1 over s plus 4 over s squared plus 4 over s cubed e to the minus s plus 4 over s cubed. This comes from, I shouldn't say that, right? But only for s bigger than 0. You find out when you're doing that integration by parts, s has to be positive in order to make this exponential not blow up when you do the integration. So there's 3 examples. What have they shown us? Well, the last example has shown us that it's going to be a pain if functions are going to have discontinuities, but we want to be able to handle them because of that tank situation I mentioned a minute ago. And the same thing if I had that electric circuit and I was constantly turning the thing on and off. Or I've had a vibrating mass spring system and it kept changing the force. Then I would have discontinuities all over the place. Well, the question might be then, how many discontinuities would we like to allow? And you might say, I don't want an infinity of discontinuities. But I want to allow that because I can envisage a function that looks like this. Periodic and going on forever. I can envisage that in an LCR circuit where the voltage is on for a while, then it's turned on. On for a while, turned on. Same thing for a vibrating mass spring system. Force on for a while, turn it on. Turn it back on. Turn it on. Turn it back on. I would like to allow those kind of functions in my discussion, but they have an infinite number of discontinuities. So I want to allow that. But I don't want to allow something that looks like the following. Don't want to allow a function that goes, has a discontinuity here, has a discontinuity here, has one here. So basically this is 1, and that's a half, and this is a quarter, and then there's an 1/8. I wouldn't want a discontinuity here, here, here. An infinite number of them. In that nice little interval between 0 and 1, I would not like to have an infinite number of discontinuities. I'm willing to allow discontinuities like this that are spread out, but I don't want them all crammed together in a finite interval, an infinite number of them. That I want to outlaw. So what I'm going to do is I'm going to demand that f of t have a finite number of discontinuities in every interval zero less than or equal to t less than or equal to t, right? Of therefore finite length. So this function would not satisfy that criteria. It's got an infinite number of discontinuities, right, between 0 and 1. This one would be allowed. You take any interval from 0 up to somewhere. There's only a finite number of discontinuities. So I'll allow that one, but I'm not allowing that one. Furthermore, I don't want discontinuities that go like this. I wouldn't want this to be in vertical asymptote. I do not want infinite discontinuities. Now that's part of what improper integrals can have. When you talk about improper integrals, you can have discontinuities, and depending upon the type of discontinuity, the improper integral might exist and it might not. I don't want them in my discussion. If I'm thinking about a tank problem, what would that mean? Good God, you suddenly drop an infinite amount of salt into the tank. Or what is it, an electric circuit? Just suddenly you had a lightning strike, okay, of infinite magnitude. Or in a vibrating mass spring system, you hit the thing infinitely hard. Well, that's not going to happen in the kind of applications I would look at. So I don't want infinite discontinuities. That's one way of saying it. Another way of saying it, demand that f of t have a finite number of discontinuities in every integral finite length, and right and left limits exist at every discontinuity. So I'm disallowing any infinite jumps in the function, because they're not realistic when it comes to my applications anyway at the moment. All right? All right. Such a function is said to be piecewise continuous. On every finite interval. 0 less than or equal to t, less than or equal to t. That's what you mean by a piecewise continuous function. On an interval. Finite number of discontinuities, and left and right limits must exist. And this one then, therefore, okay, this one is piecewise continuous. It's got one discontinuity, and it's got a left limit, and it's got a right limit. They don't have to be the same, because if they're the same, then you got a continuous function. So those are the only ones that I will allow into my discussion. Okay? All right. Another problem. Suppose for the minute that f of t is positive. Doesn't have to be, but I just want to make the discussion quite geometric for the moment. Suppose for the moment that f of t is greater than 0 for all t greater than or equal to 0. Right? So when I do the Laplace transform, I've got f of s is the integral from 0 to infinity, f of t, e to the minus st dt. Now, because this is positive, the exponential is positive, and that should be f is positive, I could interpret that to be the area under the curve. If I drew the curve, y is equal to f of t, e to the minus st. I would be talking about the area in here. And I want this integral to exist, which means that area's got to be finite. Which means, for sure, that this has got to come down and approach the t-axis. And that's not enough. Just because it comes down and approach, that's not good enough, all right? For instance, if you were to take the integral from 1 to infinity, forget about the 0 for a second, 1 to infinity, 1 over t dt, all right? You said, okay, I'm going to draw that, baby. There it is. 1 and 1. And this is talking about that area under there. Well, if you do this integral, you get the logarithm of t between 1 and infinity. And infinite. The log of infinity is infinity. So that area is not finite. If I make this a t squared, I leave you to do it, and it will be finite. The 1 over t squared is much lower than the 1 over t. It's under here. And the area under it is finite. So we've got this huge problem, all right, that this thing must come down, and it must come down fast enough so that this exists, and this thing could get large, but the question is, how large? How large could it get and still have the integral exist? And the answer is contained in the following definition. Definition. A function, f of t, is said to be of exponential order alpha, written big O for order, e to the alpha t, if there exists an m greater than 0 and a t greater than 0, such that the following is true: that the absolute value of f of t is less than m e to the alpha t for all t's bigger than big T. Now that's a pretty big definition to handle at the beginning, all right? But what it's saying graphically is the following. It's saying, you've got your f of t function here, and we're taking the absolute value. Over there, I assumed it was positive. Here, I'm not assuming that anymore. I'm saying, but you take that and saying, and draw it. Say, there it is. There's a picture of the absolute value of f of t, right? And I don't need it for, everything is for t bigger than 0. And it's saying, this function is of exponential order alpha. If you can find a t, right there, and you can find an m, such that if you draw this function, that's the function m e to the alpha t, that this guy is underneath that guy past this point. So perhaps I should draw it right there. That you can find a point beyond which this guy is underneath that guy, right? So that's that guy. So back here, it wasn't true. It doesn't say it has to always be true, but there's got to be a point beyond which this one is less than that one. So in other words, that f of t doesn't grow any faster than a constant times e to the alpha t. If you can find the m and the alpha and the t such that this is true, you say that function is of exponential order alpha. So you can't go any faster, right? Here's one that doesn't. If you told me f of t is equal to e to the t squared, that one is not of exponential alpha, order alpha. You cannot produce an alpha here so that this guy is bigger than that guy. This guy goes much faster than that guy for any alpha whatsoever. So that guy would not be of exponential order. But most of the folks you never think about, all right? Let's talk about a couple, all right? Is e to the at of exponential order something? And I would claim that he's of exponential order e to the at. Because it's e to the at less than or equal to, or less than some constant, times e to the at. The answer is yes. Choose n equal to 2. And this would be for all t bigger than 0. Big T, 0. Right? What about sine at? Is that of exponential order alpha? The answer is yes. Okay. That's less than m, for m greater than 1, right? The sign of at in absolute value is always less than a number. And I could put here e to the 0t. So alpha then is equal to 0. This function is of exponential order 0. Right? Now in the book, it talks about the exponential order of t to the n a positive integer. Right? Now reflect back to chapter 15, when we were doing all those linear differential equations. Who were the functions that we were looking at always? Weren't they t to the n's, sine at, cosine at, and e to the at, added together or multiplied together? And we're seeing those functions already. My first example, t. My second example, e to the at. Talking here, sine at, e to the at, t to the n. Right? This guy is, and it's proved in the book, he's of exponential order epsilon for any epsilon bigger than 0. And I leave you to read that and see if you can understand the discussion, right? So all the functions that we've seen so far, back in chapter 15, are definitely of exponential order, all right? What about tan, t? Is that of exponential order? The answer is no. It's not piecewise continuous in the first place, and it's not of exponential order because it bashes off to infinity every once in a while. So him's not there. Did we talk about tan t when we were doing those problems back in chapter 15? No. All right. So the ones we saw in chapter 15 are the ones that we would allow here. Right? And there's a theorem that says, if f of t is piecewise continuous, on every finite interval, zero less than or equal to t less than or equal to t, and is of exponential order alpha, then the Laplace transform of f of t exists for s bigger than alpha. All right. Theorem, proof, see the notes. It's proved in the notes. It analyzes that improper integral and proves that it converges. Now these are sufficient conditions, right? If you've got piecewise continuity, and you've got exponential order, then you've got a Laplace transform. They're not necessary. I quoted in the book that if you look at the function f of t is equal to the square root of 1 over the square root of t. Is that function of exponential order? Yes. Is it piecewise continuous? No. It's got an infinite discontinuity at t equal to 0. But it does have a transform. And you're asked to derive it in one of the exercises. All right? So if these are satisfied, then you've got it. If these conditions are not satisfied, you might still have a transform, but you might not. I think that will end that video there, and the next day I'll calculate a couple more, and then we'll talk about the inverse transform as well.